Welcome, Calculus team, to the virtual unit preview for Unit 3, Applications of Derivatives. So in this unit, we're going to be studying the applications of derivatives, as I just said. So our transfer goal, scholars should be able to use different definitions of the derivative, estimate derivatives from tables and graphs, and apply various derivative rules and properties. Scholars should also be able to solve separable differential equations, which they really won't be able to fully solve those until they learn how to integrate. But parts of it they do need to learn in this section. Understand and be able to apply the mean value theorem, and be familiar with a variety of real-world applications including related rates, optimization, and growth and decay models. The length of the unit is 11 lessons long. There is some flexibility here. I have some lessons, specifically related rates, that I'm covering over a 2-day period, and I'm also doing a unit project that's going to take a day of instruction, and I'm using an exam review for a day of instruction as well. So some teachers maybe choose not to do those items. That's all up to you. The vocabulary in the unit is pretty important, specifically the vocabulary where you see absolute, maximum, and minimum, and that entire column. Scholars need to know this language. They need to know how to read it, write it, understand that a lot of these words are command words, and know the math behind them. The other column is more they have to be able to read it, understand it, and then apply some math. But again, that first column, they need to be able to use this language in sentences. So it's very important that teachers are teaching scholars how to use the language. Assessments. I have one unit exam for this unit. I have a unit project, which is also going to be in my classroom, going to be used as a summative assessment. I have formative assessments, 2 quizzes, extreme values and mean value theorem. And then another quiz over connecting the graphs of f, the derivative, the second derivative, optimization, and related rates. Also, you can use exit tickets every day as an assessment. That's all up to you. So the extreme value theorem. So scholars need to know when the extreme value theorem applies. They can abbreviate, by the way, EVT. The big thing is they have to know to check for conditions. So the extreme value theorem, the only condition is that the function is continuous on a closed interval. I stress very hard in my classrooms that closed interval has to apply, has to be there for the extreme value theorem to apply. Differentiability is not required. As you can see from the graphic I have, there are 2 points where this function is not differentiable. However, both of those points are a maximum and a minimum. So extreme value theorem only needs an included endpoints to apply. The mean value theorem, on the other side, that is not the case. Scholars need to know the conditions of continuous and differentiable, and they have to state both conditions. I know in the past that we have said that if a function is differentiable, it is implied that the function is also continuous, but on last year's AP exam, they did not accept that, and so while grading, readers did not give credit if scholars only said differentiable. Scholars had to say both continuous and differentiable. I cannot stress that enough. And so scholars also need to understand what the mean value theorem allows us to do in calculus. And this is going to help very much if scholars just understand this concept that we can use the slope of the secant line to approximate the slope of the tangent line. And that's really how we're finding tangent line approximations, because it's usually going to come up in a data table, this type of question. Oh, tangent line approximations. So we'll be assessing this probably in the free response question on the AP exam. It can be assessed in the multiple choice, but I'm pretty sure you're going to see it in the free response. So let's make sure that we are looking in the archive, Unit 3, Lesson 3 lessons that I have in Blackboard. You will not see an annotated model lesson for tangent line approximations, but you will find one in the archive lesson. Please make sure you go and check those archives out. Sign charts, big deal. This unit is heavily uses sign charts. And I just want to let all teachers know that sign charts are a useful tool, but they are not the end-all be-all. You must teach your scholars how to show their work and use their work to write a nice, clean justification statement using the language that we talked about earlier in vocabulary. Scholars must mention all critical points, and if we're talking about a second derivative, all points of inflection. And they need to make sure that when they talk about a point of inflection, that it's either a potential point of inflection or they have the justification to now qualify that point to be a point of inflection, which requires a sign change. However, sign changes are not good enough justification. So we have graphical analysis, as I've mentioned several times, vocabulary. We don't want scholars to say that a function is increasing when they really should have said the word positive. If they mix up this language on the AP Calculus exam, they will earn no credit for their justification. So looking at this graph to the side, on the interval from 0 to 2, f is increasing, f prime is positive. Do you see the difference in the vocabulary? Scholars sometimes don't understand what that difference is. It's very important that we teach that to them. So increasing and decreasing refer to slope of f, and positive and negative refer to the values above or below the x-axis, function values, or if I'm talking about f prime, derivative values, positive and negative. This type of question will show up on a calculator inactive free response question. These questions will also show up in the multiple choice frequently. Very heavily tested skill. Okay, extreme values and concavity. In the archives, I found this beautiful graph. It's a table, whatever we want to call it, that has it has all the language we need. It has all the signs we need, everything we need to really analyze a graph. And scholars really seem to grab onto this. I have it in the archives, and I can also send it if anyone just wants to reach out and ask me for it. So on here, I want to go back to the sign change. Remember, I said a few minutes ago, a point of inflection, we have to say there is a sign change in order to be, justifying that point of inflection. But just saying a sign change is just not enough. If I want to talk about a point of inflection, I need to say that f double prime changes from positive to negative, or vice versa. If I want to talk about a maximum, I need to say that f changes from increasing to decreasing. However, if I want to say there's a maximum and talk about f prime, I can. Now I have to say changes from positive to negative. It's very important that we use increasing and positive or decreasing and negative in the right context. If we're going to name f, we must say increasing, decreasing. If we're going to name f prime, we must say positive, negative. I hope you are able to see the difference. If not, please reach out to me. Optimization. Optimization is a skill that scholars tend to struggle with. So when I'm teaching optimization, I try to take a business stance and say, well, if I'm building a box that holds cereal or a fish tank or some type of prism, I want to maximize my profits. I want to sell this box. I want to maximize my profits but minimize the costs. So I want to build this box using the least amount of material so that I can make the most money. And so they seem to understand this. I think the biggest problem is the word optimization. They really don't understand the definition of it. So take a few minutes, explain what optimization means, take a business stance from it, and they might be more equipped to answer optimization questions. Then they understand, oh, I'm trying to find the max. Oh, I'm trying to find the min. Things like that. So, and this type of question will show up on the multiple choice. I have not seen it on a free response in quite some time. It's not a very high leverage skill, but it's still part of our curriculum. It's still part of this unit, and it's still tested. So let's go ahead and make sure we teach it. The related rates lesson is the lesson that I talked about earlier that I'm teaching over a 2-day time period. Scholars need a little extra time to really internalize what related rates is about. And I start off talking about related rates as something that changes over time. So the two things that we're going to put together is time and perimeter, volume, area, things of that nature. And how do things change as time progresses? And so I really like to break the shapes down. Triangles is tested a lot because you have Pythagorean's theorem and they have to come up with their own triangle. But triangles are also assessed using similar figures. So triangles is just a really good thing to make sure you teach your kids using both similar figures and the Pythagorean theorem. This is probably a skill that's going to show up on the multiple choice. I haven't really seen it on the free response for a little while, a couple of years. That doesn't mean it's not going to show up next year in the free response, but I think it's going to be more assessed in the multiple choice calculator active. And then we have the Unit 3 project. I encourage everyone to watch the virtual roundtable held on September 27th for a walkthrough of the project. If you attended that roundtable, great for you. If you want to reference the virtual roundtable again, even if you attended that roundtable, you can still look online. It's posted in Blackboard. So let's talk about the unit project for a minute. I have it broken down into 4 parts. The first part is a project proposal. So I'm going to give out the project expectations to scholars in my second lesson of this unit. I usually like to give it out in the first lesson, but there's time constraints on my first lesson this year, so second lesson they're getting it. By the end of the week, the second week, they have to turn their project proposal into me. And the project proposal is nothing more than them taking a picture of their container, some type of vase that has some curves. And it has to have a flat bottom, and it must be see-through. So their container is very important because that's what they're going to gather all their data using. Oh, and their data. So basically, scholars are going to be filling their container with water. And so they have to also select a scoop, but I'm not requiring them to send me a picture of the scoop. I want my scholars to struggle with the scoop a little bit. I want them to pick a scoop that's too big maybe for a minute and say, hey, I'm only getting 2 data points from this. This doesn't make sense. So anyway, they're going to fill the vase, container with water and then take note of every time they fill the container with another scoop of water, and that's going to be their data points. So the X values are going to be the number of scoops, and the Y values are going to be the height of the water within the container. And so with this data, the scholars are then going to sketch a graph, and their graph should be continuous because they're continuously filling water in the container. Their graph should have included endpoints, so the extreme value theorem will apply. And now their graph is continuous, and their graph is going to be differentiable. There shouldn't be any sharp turns or vertical tangents or discontinuities. And so now we're going to talk about extreme value theorem. We're going to talk about the mean value theorem. When are we going to talk about this? Well, during the discussion and analysis in class, which is my last lesson I have in the unit plan. We'll also talk about concavity, maxes and mins, points of inflection, intervals of increasing and decreasing. Basically everything in the unit is going to be assessed on this unit project. Almost everything in the unit. And in my class, I'm going to have this discussion and analysis, and then they're going to fill out a form, which I have attached in Blackboard, that says, oh, what is the max and min? Does the mean value theorem apply? Explain why the mean value theorem applies. And it's just a very nice culmination of the unit. And then after that, scholars can take all of their data, their graph, their discussion and analysis, and write a nice essay over the project. And so I think it's a great way to sum up the project, to sum up the unit. And I look forward to seeing what your scholars are doing, and I will definitely be posting some artifacts from my classroom this year. All right, so that was all of Unit 3. If you have any questions, please contact me. If you want to tell me you have found some other good stuff and maybe we can change the project around, whatever you want to do, please contact me and let me know what you have available. I love working with you, and I'll see you next time.